Okay, yeah, please. Thanks, Brian.
So first of all, I want to thank my advisor, Jeff, giving me this opportunity to give a talk here. Okay, thank you. And my topic is the stability of the generalized BC soliton. And recently I posted it on the archive, and I think that it will be an updated version recently, maybe in these 2 weeks. Yeah. Okay. So this is my outline. I will first present my motivation and introduce the generalized Einstein-Hilbert function. I think this is covered maybe a year ago in this seminar. And the second version formula. And lastly, I will mention my main result about the linear stability and the dynamical stability. Okay, so this is my outline. Okay, so let me start at my motivation. Our motivation is coming from the Ricci flow. As we know, the Perelman entropy lambda tilde. Yeah, here I denote lambda tilde is in order to distinguish what I did for beta case. So here lambda tilde G is the infimia of the functional R plus gradient F squared exponential minus F dVg. And you focus that the F volume exponential F dVg is always to be 1. Yes, it's somehow like a normalization. And the Perelman will tell you that the Ricci flow can be interpreted as a gradient flow of the functional lambda tilde. Yeah, on the space of the matrix modular diffeomorphism. And what he did is he computed the first variation. And the first variation of lambda tilde is given by the inner product with H and Ricci plus hash and F. And here, we should note that the, sorry, this should be FG. The minimizer F of lambda tilde is always achieved and it is unique. Okay. And because this lambda tilde is diffeomorphism invariant, actually, we can deduce that if we plug in the Ricci flow, so let's say H is minus 2 Ricci, then this should be a complete square in the first variation formula. And sorry, this is positive sign because here we have minus here. Okay, so this quantity is always to be non-negative. In other words, it shows that this lambda tilde is decreasing along the Ricci flow, and a steady gradient Ricci soliton, if this is 0, they are critical points. Okay. So this is what Perelman did, and moreover, we can compute the second variation formula. And this is the result from Tao and Hamilton and Yeoman. They computed the second variation of lambda tilde on the critical point, which is compared Ricci soliton, compared Ricci flat manifold, is given by the operator L. And this operator L is half of Laplacian plus divergent star divergent H plus half of Hessian BH and plus the cross term about the Riemann curvature. Maybe I should say more precisely, this quantity, sorry, I opened the wrong field, sorry, whoops. Give me a second. Okay, sorry. So this quantity is in fact be defined like Riemann H Ij is R I K L J times H K L. Okay. And here, this VH will satisfy the PDE. Laplacian VH is divergent H. Okay, this is what our Hamilton element did. And we would like to know that on a critical point, whether the manifold are stable or not. It means that if the second variation formula is non-negative, non-negative or non-positive, we want to derive some result about this. But it's hard to argue this directly. So our idea is we will decompose our variational space. Intuitive, we will write our variation space S2M, yes, any symmetric to tensor, to be some kernel divergent part and the image divergent star part. And okay, this is for this part, image divergent star part. We can deduce that it's actually coming from some Lie derivative. Therefore, if your variational space, if you consider the variational in this space, it's actually deduced that your GT is the pullback of some diffeomorphism. FT is some diffeomorphism. So because our lambda is diffeomorphism invariance, our second variation will vanish on this part. And therefore, we only need to consider our variation space to be the element lies in the kernel divergent plot. And this is really a good thing because if your H lies in the kernel of divergent, then Laplacian VH is 0. So VH is vanished and divergent H is vanished. So actually our operator L in this case is to be the half of Laplacian plus the Riemann curvature tensor. Okay. So they will define, okay, not define. Okay, so we will introduce the additional noise Laplacian, which is defined as Laplacian H plus 2 of curvature tensor term minus Ricci compose H minus H compose Ricci. And because on the critical point of lambda tilde, they are Ricci flat matrix, so we don't have these two terms. And then this is exactly what I wrote here about L, operator L. So we will say that a critical point G of lambda tilde is linearly stable if the operator, the additional with Laplacian, is non-positive. Okay. Okay, so far we know that we have a concept that if Laplacian L is non-positive, then it seems that the lambda tilde is a local maximum, and we call this kind of stability to be the linear stability. So let me mention here. We suppose our GRF is a compact Ricci matrix, and we say that this GRF is linearly stable, means that the additional with Laplacian are non-positive. Okay. So this is the notion about the linear stability. On the other hand, we call that the GRF is dynamical stable if okay, let me write down a picture. So if this is GRF, then we consider any neighborhood around this. Yeah, in the space of the Riemann matrix. So I think later we will use this capital N to denote the space of Riemann matrix. Yeah, space of matrix. So that says this neighborhood lies in the M. Okay. We say that GRF is dynamically scalable if for any such neighborhood U, we have a smaller neighborhood, say maybe V. V is containing U. Then any Ricci flow starting in V, some element in V, say maybe G0, the Ricci flow will exist for all time, and it will stop at some point, G infinity in U, and this G infinity is also Ricci flat. Okay. So there are two different concepts about the stability. The first one is linear stable. It means that the additional waves topology is non-positive. Then the second thing is about the dynamical stability. Is some stability property related to the Ricci flow.
So wait, sorry.
Yes.
Why don't you, in the first notion in dynamical stability, why don't you impose that the Ricci flow converges to the Ricci flat metric that you have fixed? Why can I?
Okay, I understand your point. Because there are some cases that the Ricci flow may not flow back to our original metric. Yes, so we extend this concept to say, okay, we will start at some Ricci flat metric. Yes.
Yeah, why do you need to do that? I mean, for me, it will be more natural if in any neighborhood, I mean, if there exists a neighborhood such that any initial metric takes the Ricci flow to the Ricci flat metric, but not to another one. So I just, there are examples like this.
So far, I think that there are no example coming in my mind, because what Hamilton did, they will say, okay, they will converge to original one, but I think
no, I mean, anytime you have continuous families of Ricci flat, right, this is somehow the best you can hope for. Right, so for instance, even just like on K3 surfaces, you just have like a family of Calabi-Yau metrics, a smooth family. You perturb away from a given one, maybe you just perturb in the family. You don't expect to converge to the original one, just to something in the smooth family.
Okay.
Yeah, and as you will see that in my work, we will not guarantee that our generalized Ricci flow will flow back to our original metric. Yeah. Okay. So this is the dynamical stability.
But on a K3 surface, you flow through a given Keller class, right? And the Ricci flat metric is unique in that class.
Well, yeah. So Keller Ricci flow.
I think this phenomenon should happen when you have automorphism, but Ricci flat.
No, even because in any case, the result as he states it is just for Ricci flow. Of course, Keller Ricci flow will preserve the class and converge to a unique limit, as you say. But regular Ricci flow, you can change the Keller class, for instance.
But this is actually a good example, because you may perturb the initial Ricci flat metric by deforming the Keller class, and then you see that the limit will not go to the original.
Exactly. Yeah. Exactly.
Okay. So this is the result from Hasselhofer or session. So they say that, okay, sorry, let me come from one thing. So first of all, if you look at the definition about these two stability, you can see that if you are dynamical stability, it implies the linear stability. This is due to the fact that if we're rounding the Ricci flow, then the lambda is non-decreasing. So if you have a dynamical stability, then, okay, so let's say lambda G infinity should be bigger than lambda G0. But because the G infinity is Ricci flat, their entropy should be 0. Yes, I get yes. And this is the same as with GRF. In other words, it says that the lambda at the center should be the maximum, and it implies that they are linear stable. Okay. But the question is, can we say that the linear stable will imply the dynamical stable? This is the main question. So here, Hutchhofer and Sesson prove that this is actually true. And the precise statement is, okay, if I say k is greater or equal to 3, and the additional is Laplacian at GRF is non-positive, then for every ck neighborhood we have a ck plus 2 neighborhood B. I should not say content because it's not precise, of GRF such that the Ricci flow starting in V will exist and stay in U for all time and converge exponentially to some Ricci flat matrix in U. Okay. And Hutchhofer also proved about the dynamical unstable property. They say that, okay, if the additional is Laplacian is positive at some point, then we have a non-trivial engine solution. I.e., it means that we have a non-trivial Ricci flow GT that if you flow back to minus infinity, it will be the Ricci flat matrix GRF. Okay, so this is our motivation. We try to deduce the second variation formula and find some linear stable examples in our case, and then we want to show that these two concepts, dynamical stability and linear stability, are equivalent. Okay, this is our goal. Okay, good. So let me move on. And okay, so let me review the generalized Einstein-Hilbert functional. In the following, I will fix that our M is a smooth manifold and E is an exact Corey algebra over M. So the generalized Einstein-Hilbert functional is given by the function, the integration about R minus 1 over 12 h squared plus hash f squared in terms of the F volume. And similarly, we define our entropy lambda to be the infima of capital F with the normalization that the F volume is always to be 1. Okay. And similar to the previous case, this minimizer F is always achieved and is always uniquely achieved. And our lambda will be the lowest eigenvalue of the operator minus 4 Laplacian plus R minus 1 over 12 h squared. And moreover, our lambda is given by this equation, R minus 1 over 12 h squared plus 2 Laplacian F minus gradient F squared. This is really useful. Okay. Okay, so first of all, let me recall the first version formula. We fix our convention that the derivative of G is H and the derivative of HT is dk. So, and Ft will be the minimizer. Okay, and the first version derivative of lambda is given by the inner product of minus Ricci plus 1/4 h squared minus hash f with h, and the inner product of d star h plus I gradient of h with k. Okay, I think this is shown before. Okay, And okay. So let me recall what is the generalized Ricci flow. If you fix a background closed street from H0, a one-parameter family of the generalized matrix GT, generalized matrix GT, is called a generalized Ricci flow if the derivative of G is minus 2 Hessian plus half of H squared. Sorry, I just say that in here H squared XY is the inner product of IXH and IXY. Sorry, IYH. Okay. And the derivative of B will be minus D star H. Yeah, again, here H is H0 plus DB. Okay. So, okay. So next, let me define the steady generalized Ricci soliton. We say that our MGH is a steady generalized Ricci soliton if you have some vector field X and a closed tube form X, a closed tube form K, such that 0 is the Ricci minus 104 H squared plus half of the LXG, and 0 is half of D star H plus half of IXH plus K. And in particular, we will say that our soliton is a gradient generalized Ricci soliton if X is gradient F for some function F. And in the following, we will always consider the case that X is gradient F and K is 0. So in the following part, we will say MGH is a steady generalized Ricci soliton if 0 is Ricci minus half of H squared plus Hessian F, and 0 is D star H plus I gradient FH. Okay. Sorry. Okay. And we will say that MGH is a general Einstein if it is a soliton, but here F is a constant. So in other words, they satisfy that 0 is Ricci minus half, sorry, not half, 1/4 H squared, and 0 is D star H. Okay, so here we see that our soliton will satisfy this quantity. Then back to the first variation formula. Back to first variation formula. This is exactly the quantity shown here. So similar to the parallel case, we can show that the first variation of derivative of lambda under generalized Ricci flow, it should be non-negative. Okay, this is also due to the fact that our lambda is diffeomorphism invariant. Okay, so our lambda is always increasing, and it's 0 unless you are in a compact steady soliton. Okay, so far this is a kind of review what we did in the first variation formula. So later I will move to the second variation formula. So in this case, let me fix my convention that, yeah, again, the derivative of G is H and the derivative of H is dk and the derivative of F is phi. And we introduce, okay, it's a little bit messy, but yeah, I will mention the data if it appears. Okay, so this is our notation. To compute the second variation formula, we first have two computation results. Okay, so first I want to divide the derivative of the Ricci minus 1 for x squared plus a hash f. Then you can, this is actually coming from the standard computation about the variation formula. As you can see, this will be partial derivative of Ricci is, for example, the derivative of Ricci maybe is, I think it's half of Laplace h plus something else. Then after simplification, you will derive this. Okay, and the second quantity is that the Laplace f. Here, let me see. Laplace f is Laplace minus gradient f dot gradient. Okay, Laplace h minus gradient f h. Okay. Maybe I should not use h. Laplace f u. Okay. Okay, so how to derive this result? This is due to the fact that our lambda can be expressed as r minus 112 x squared plus 2 Laplace f and minus gradient f squared. And because we are in the critical point, so the derivative of lambda is always 0. And this should be the derivative of this quantity. Then again, if you plug in the variation formula about the lambda, h squared, and f, then after simplification, you will derive this result. Okay. So based on these two computation results, we can write down our second variation formula on a compact steady generalized gradient generalized Ricci solution. It's a little bit long and messy, and we will try to simplify it later. But here it's just, this is the a complete statement. The second derivative of lambda is given by this 4 line, and okay, so these 2 lines are some quantity related to h, and here we have a cross term hij dkiab hjab, and this terms is the hardest part. The hardest part. I will explain this later. And minus 1/6 dk squared. This is the part only related to dk, and minus half of gradient vhk squared. And this term is actually coming from vhk is coming from the trace minus 2v in the computation. So based on our previous computation result, this VHK is the unique solution. Yeah, this unique means that it uniques up to a constant. This is the solution about this PDE. Okay, so why I think this is the hardest part. Sorry, we will see this later, and you can see that this 2 quantity is always be non-positive. So this is not a big deal. And this is somehow something only related to h. And this part can be compared to our previous case in the lambda entropy, param entropy. Because this is only depending on h. But how to estimate this is the hardest one. Okay, any questions so far? Okay, good. So here, let me briefly explain how to derive this formula. It's just a simple computation. Yeah. So So to compute the second variation formula, we should start at the first variation formula. And then because we are in the soliton, then after taking the derivative, okay, here I use the notation that delta means the derivative. Okay, it's just for convenience. Okay, so if I take this, then we need to compute this part and this part. And this part is actually coming from our equation 4, the first computation result we mentioned before. So this is done. And for the second part, actually they are the same. If you compute using the variation formula directly and plugging into your equation, then yeah, I should say that this is coming from lots of integration by part, and we will use the soliton equation to simplify it. Okay, and similar to this case. Okay, so for the second part here, we will, after a long computation, lots of integration by part, we will see that the second quantity is actually coming from the half of hk or hkij, dk or ij, expression minus f dvg minus 1/6 dk squared, expression minus f dvg, and some term, we don't want to see it. Okay. So what is this one? This one, to deal with this one, we can define VHK to be the trace of -2 phi. Then, okay, so then because the inner product of DKH, we recall that a project F of trace -2 phi is divergent FH minus 1/6 DKH. So we can rewrite DKH in terms of VHK. So this will left with minus of half of gradient VHK squared and minus half of Hessian VHK with H extension F dVg, and this term can be cancelled out with this one. Okay, so we derive our second variation formula. Okay, it's just a sketch of proof, and it's actually nothing but using lots of integration by part. Okay, but you can see that this is hard to estimate because yeah, it's too long and there are some cross term. And so next time we want to simplify it. But first of all, we want to find an operator to express our second variation formula, just that what we did in the lambda tilde case. We will have the operator L. So what's the operator corresponding to the second variation formula here? Okay, so this is our goal. And okay, so first we will fix our inner product like this. We say we have H1K1 VH1K1 times inner product with H2K2 H2K2 means that the standard inner product with symmetric 2 tensor and Q form, Q form plus the multiplication about 2 functions in terms of the F volume. Okay, so to write down our second variation formula, we plan to because there are some cross term here. So we hope that we can find an operator n. Okay, this is what we hope. Somehow, yes. Okay, but NHK contains is an operator depending on H and K. So we will try to write it to be okay, some operator in terms of H plus some operator in terms of K. CK plus DH slicing symmetric 2 tensor times 2. Yes, this is our goal. We try to distinguish the symmetric 2 tensor power and the 2 form power. And this is the ABCD we found. Yes. Okay. So in fact, how to derive this is you can let me use C2 as a motivation. Oh, maybe I should start at okay. To figure out to find A is simple because A is the term only depends on the symmetric 2 tensor power. So we just write yes, we can define operator to be here. This is our H, our AH. And similarly for the DK part, we use a integration by part to figure out. Okay, sorry, this is wrong notation. Yeah. This is B and this is C. Okay, so the hardest one is how to find the cross term. The cross term we have is Hij dkiab sjab. This solution minus fdvg. Okay. So first you can define ck like this. You can define ck like this. This is easy because when you inner product ck with h, this is nothing but half of this quantity. So we have this result, but for other part we have dh inner product with k. So we just use the integration by part to transform d to other side and derive our dh component. Yes. So this is our final result. If you define your operator like this, HK, VHK map to AH plus CK, BK plus DHN, Laplace of VHK half, then we can express our second version of formula in terms of the operator n. Yes. And moreover, n is self-adjoint because, as I explained above, you can argue that this term is clearly self-adjoint and similar to BK, and also this one. This three terms are clearly self-adjoint. For the cross term, you know that the inner product of CK and H is the same as the inner product of DH with K term. This property will imply that our operator n is self-adjoint. Yes. Okay. So we generalize we extend the result about the lambda tilde entropy, the second version formula of lambda tilde entropy to our case. Okay. Any questions so far? Okay, so the next thing we want to do is we want to estimate our second variation formula. Okay, let me repeat again the definition about the linear stability. That MGHF be a steady gradient generalized Ricci solitary. We say that this solitary is stable if its second variation is non-positive. Okay, first we can see a spatial case. If H is 0, if H is 0, it means that we are in a gradient steady Ricci solitary. And in fact, this is Ricci flat, right? Because F is also 0 in this case. So if you look at our second variation formula, and H is 0. Let me back to here. If H is 0, we don't have this 2 power, and we also this 3 this 3 power will be removed. Then we only left with these 2 lines. Okay, as you can see, this is always be non-positive. So you only left with you only need to consider these 2 lines, and moreover, this quantity is somehow related to the Ricci-Nova's Laplacian as we have in the previous case. Okay, so if you just focus on the kernel divergent part, if H only lies in the kernel divergent part, our second variation formula of lambda is actually to be the half of Ricci-Nova's Laplacian HH minus 1 over 6dk squared is function f dvg. So it is stable if and only if the Ricci-Nova's Laplacian is non-positive. And this is exactly the same as the previous case. And it's not surprising because, yeah, it must be true because we are in the same critical point. Okay. So later we will see that why we only need to consider kernel divergent part in this case also. But here, this is our result in the H0 case. So this case is trivial. This case is trivial, and therefore we will consider the generalized Einstein manifold. If you are consider generalized Einstein manifold, it means that F is a constant. Then you don't need to consider the F volume, just consider the standard volume form, and then our second variation formula can be rewritten as like this. Okay, here I transform the Laplacian to be additional with Laplacian by using the property about the general Einstein manifold equation. Okay, this is due to a fact that, okay, let me scroll up a little bit. Here, if you are in general Einstein case, then this is actually the Ricci curvature term. Then you can express this 3 quantity to be the Ricci-Nova's Laplacian. Okay. Okay, so finally we can rewrite our second variation formula like this. Okay, so again we will face the same question: how to figure out the cross term. And yes, to test the linear stability, we may also try to decompose our variational space properly. So in previous case, we can decompose our symmetric to tensor to be the kernel divergent part with the image divergent star. And I feel that the motivation to do so is this part will induce the diffeomorphism in diffeomorphism part. So actually this part is trivial. Therefore, we only need to consider this quantity. But how can we do it in our case? In our case, our variational space will be symmetric to tensor times the omega 2 form. How to decompose it? Unfortunately, the Rubio and Tipler generalized the Ibc slice theory to divide the generalized slice theory, and they provide a motivation to me how to decompose this space. So I will review their result briefly here. Okay, so this is our notation. The space GM contains all generalized metric, and M is the space of Riemann metric, and lambda is the space of isotropic splitting. And we recall that if you fix some quantity in lambda, then we can see that our current algebra is nothing but T star, and the generalized metric is M times omega squared, and automorphism can be expressed as diffeomorphism and the B field. And they satisfy that B star H is H minus dB. Okay, and this is on notation. If you take a derivative about the automorphism, we have X and omega, and dIXH plus omega is 0. Okay, and to explain the proof, we will use this action. The action on the generalized metric. If you have phi b here, then you can act it to your generalized metric to derive another GB. And later we will restrict this action on GDFH times GM, and we call this to be the GDFH action. Okay. So before we move it, we move to the next part, let me mention one more thing. If you denote H prime to be the straight form corresponding to V star B minus B, then what do you have? Okay, if you fix, again, if you fix the background metric, background three form H0, and H prime can be say H0 plus D V star B minus capital B. Okay. Then okay, because here, if you say your phi b lies in G diff H, then V star H will be H0 minus dB. So we have V star H0 plus D V star B, which tells you that it will be V star of H0 plus dB. And if I say this is the level corresponding to a 3-form H, then the 3-form corresponding to V star B minus B is nothing but the pullback of H. So you can see that if you consider the generalized matrix here, G with GGB, and the action and the orbit respect to this action, orbit respect to this action, then every matrix here, G S maybe, yeah, GS, GSBS, it will corresponding to phi star G, phi star H for some phi. Okay, this is what I want to say. Okay, so let me mention their result. If you say the isotropic group, isotropic group to be this one with respect to the G-diff action, then the result is that we can find if you fix a generalized matrix, we have a ILH sum-manifold as G of GM such that these three conditions will satisfy. Here we will not touch on the ILH manifold. So we can imagine that this is a sum-manifold. And what does this three property say? It says that if you plug in an isotropic group, then it should be invariant. And if you plug in some diffeomorphism that intercept with the original slice is empty, then this F must lie in an isotropic group. And the third property somehow says that locally, you can express our generalized matrix GM to be the slice times orbit. Okay, so this is the generalization about the Ibc Flow slice theory. And they call it to be a generalized slice theory. Okay. Okay, and the idea about the proof is like, okay. So if you fix a generalized matrix G, and we consider its orbit under this action. So this is OG with G diff H until G. And they found that the tangent space of this orbit can be expressed as some operator A for some operator, sorry. For some operator A. Okay, and they can extend to the whole orbit. And by computation, they can also they compute the A star operator, the adjoint of A. By computing that one, they will try to define a normal bundle. Normal bundle nu G. Nu G will be the kernel of A star. And after that, if we have a normal bundle, then we can integrate it so that we will generate the slice SG. Okay, this is the idea of their proof. Actually, this is the idea from Ibc and Pallas. But there are the hardest one is that how to find the operator A star. And Rubio and Tipler work on it and find the proper operator. Okay, this is their contribution. Okay, but in our case, we cannot apply their result directly because you can see that in their proof they rely on they've computed the A star operator, and this will related to the inner product, L2 inner product they use. But in our case, we consider the F value. So it means that we will use the different L2 product. So okay, so in our case, we need to consider the F twist inner product. In other words, we will have exclamation minus F here. But fortunately, if you say our F is isometry invariant, then revise the proof carefully, we can derive the same result. And this is the slide we want to use. Okay. Okay, and how to use this result is, okay. This is the idea. Somehow the third condition tells you that our slice can be decomposed, our generalized matrix can be decomposed as the part in the slice and the part in the orbit. So the tangent space should be decomposed by the tangent space in the slice and the tangent space in the orbit. And we show here that somehow if you slice in the orbits, they are trivial. So this part is trivial. In other words, we only need to consider our variation lies in the tangent space of the slice. And if you look at the proof carefully, we can write down Y is TGSGF. But okay, so in order to express it, we will fix our background string from H0, and we can choose H0 property so that we can say, okay, in G, we will force that our B is to be 0. Then in this case, we can express our tangent space of the slice to be the variation that the div FH will be the half of Kij Hij and D star FK is 0. Sorry. Here D star F is up DK. Sorry. This is only J component. I think it should be passed. Okay. This is D star K. And K is orthogonal to the harmony 2 form. Okay, so we have some relation between divergent H and K. This is the key point. Then back to the generalized Einstein case, if you force that F is 0, then by the Hodge theory, we can say that K is actually D star of something. Okay, so this is the non-trivial variation we need to consider. Okay, this is the non-trivial part. Okay, so again, you can see that if you are in the H0 case, if H is 0, this quantity is actually 0. So this is the reason why I say that in the previous case, in the H0 case, where is it? in the H0 case, we can also consider our H lies in the kernel divergent part. Then everything is back to the previous case because this quantity is always be non-positive. Okay, any question?
What you call D star F, is this the adjoint of D with respect to the conformal rescale metric?
Oh, yes. Okay. So here, if I compute the formal adjoint, in the Ruby on tabular case, they only use the standard L2 product. But in our case, we will, our formal adjoint will depend on F. Yes. So you can see that our tangent space of slide will depend on F here and here. But if I force the F is 0, then you don't need to consider F. But maybe this is the reason why we consider the general Einstein manifold case here. Okay, so let me write down our decomposition carefully. You can see that if I just focus on this space, this is not good enough. So I will try to find another space to decompose our variational space like this. We have V plus V1. Direct sum about is orthogonal complement. Yeah, again here this complement is with respect to let me write down here with respect to the inner product of exclamation minus FDVG. Okay. And here, okay, V is coming from LXG and K is minus omega, where X and omega is coming from the GDF H part. So actually, this is the image of AF plus star. This is the trivial one, trivial part. This is the trivial part. Okay, so before I mention other space, let me explain more carefully why this is the trivial part here. So by definition, if HK lies in V, we have a family of diffeomorphism GT such that the derivative of GT lies in HK. And here, GT BT will be FT star G minus D minus BT because here H is LXG. So in fact, our FGT is constructed by the diffeomorphism for some FT. And K is minus omega. Yeah. Then the corresponding three-form HT is coming from H plus D of minus BDT. And because FT-BT lies in the GDF H part, as I computed before, this is nothing but FT star H. And this is the reason why the second variational will vanish in this part due to the diffeomorphism grammar. Yeah. Okay, so this part is trivial. And to figure out V1 part, I think it's intuitive in the previous case. If you have a arbitrary symmetric to tensor, and then you want to decompose this space, the first thing you may want to try is you want to find a conformal. You want to consider the conformal part. So this is the motivation how I define V1. I define V1 to be the conformal part UG and K when n is greater than 4. But in three-dimensional case, we will define this K more carefully to be the minus of d star omega dvg. And here omega is some function. And we will explain later why I define it like this. And then by the direct computation in terms of the inner product, we can see that our B perm intersection with V1 perm will be H0. Here, H is trace-free and divergent-free. And usually we will denote this kind of property. Say, okay, this will say that H lies in the TTG. And TTG is the space that divergence is free and trace is free. Okay. So once we decompose our variational space like this one, and because our V is trivial part, we only need to consider these two space and their cross term. So in the following, it suffices to consider to check for variational lies in this space, where UGK lies in V1 and H0 lies in this part. Okay, so let's check for it. The first one we want to check is that the second variational lies in this part, V1 part, is always non-positive without any condition. Okay, so let me plug in UGK in our second variation formula. We will, okay, this is what we will derive. And okay, so here again, the bad term here is the cross term. You can see that this is negative, negative, negative. Every term is negative instead of this one. And my motivation is that we try to use Cauchy-Schwarz to give a bound about this. And first, we can see that how to write it. Okay, we can use Cauchy-Schwarz here, right? Because we have H and DK here, so directly using Cauchy-Schwarz, we can give this bound. But unfortunately, 1/6 is too small. This is too small, so that we cannot bound it. But fortunately, we know that the gradient V is a solution satisfied. The Laplacian V is the Laplacian U minus 1/6 DKH, and this is somehow related to this one. So we just check for what is gradient U with gradient V. Gradient U, gradient V by integration by part is minus about U Laplacian U and minus U/6 DKH. Okay, good. So this is exactly the term we want to care for. So in summary, because of this result, we can also use this quantity to give a bound about the cross term. Then after choosing proper constant, this is the term I choose, and this is the term I pick. Then after choosing proper constant, we can show that our second variation formula is bounded by this constant times gradient U squared. Actually, it depends on you to choose this quantity. And you can see that this term is non-positive if n is greater than 4. So the critical point lies in when n is free case. You can check yourself that I mentioned that these two constants you can pick by yourself, but you will find that no matter what constant you pick, you cannot bound for n equals to 3 case. So we need to discuss separately between the n greater than 4 case and the n is 3 case. Okay, then back to our definition about V1. This is also the reason why we define V1 separately when n is 3 case. Okay, so let's focus on n is 3 case. Before I mentioned it, let me recall that when n is 3 case, this is really spatial because our general answer manifold, in the general answer manifold, our scalar curvature and S square is constant. So when in n is 3 case, our generalized Einstein manifold is nothing but S3. Okay, we only have S3. So to continue the proof of lemma, we may suppose that our MG is a unit sphere. Then if it is a unit sphere, and we write H to be 2 dVg, then the sectional curvature is constant and it should be 1. Then we can rewrite our second version formula in terms of this quantity. Yeah, it's a long computation, but yeah. Oh, here, sorry, I forgot to mention. Because in the street form, we can express dk to be per side dvg. So this is how we simplify it. Okay. And next, because you see, Laplacian V is a solution of divergent twice H minus 2 per C. So here, if I say H is UG, this quantity is Laplacian U. So we may hope that if per psi is Laplacian of some function, then we can express V to be U minus 2 omega. Therefore, in 3-dimensional case, we will write or we will define our V1 in terms of minus d star omega dvg, because once we define like this, our dk will be the Laplacian omega dvg. Then we can express our V. Therefore, anything will be returning to the quantity related to U and omega. Okay. So the next step is how to estimate this. Because we are in the unit sphere case, we try to work on it. What is Laplacian omega? To figure out, we will consider the eigenvalue of the Laplace operator on the unit sphere. And chi k will be its corresponding eigenfunction. As we know, this view k is k times k plus 2, and k is starting at 0. Then, yeah, we can expand our u and omega in terms of the eigenfunction. So we may write u to be the sum of ai chi I, and omega to be a sum of bj chi j. Then by plugging this into our second version formula, it's going to be summation of chi I squared in terms of this integration. Okay, so if I can prove that this is always to be non-positive, then we are done. But unfortunately, if you do use the Cauchy-Schwarz, this property to be non-positive if your mu I lies between 0 and 3, or your mu I is greater than 8. But as we recall, your eigenvalue is k times k plus 2. So the critical point, if k is 0 is 0, if k is 1 is 3, and k is 2 is 8. So exactly, they satisfy the condition here. Therefore, we can show that this is non-positive. And actually, you will find the kernel of the variational in terms of here, because you can see that if chi1 and chi2 will match the critical point. So we may have some term in the kernel of variation. And you can, so in fact, the three-dimensional case is really spatial. And there's non-trivial variation that they won't change. They won't change the lambda entropy. Okay. In other words, it will say that maybe there are some non-trivial Ricci solitons. Non-trivial steady generalized Ricci soliton. Okay. Any question? Okay, so let me move on.
Maybe it's just worth mentioning that not only might there be solitons, but there are, right? I mean,
Yeah, they are.
This kernel is really corresponding to an actual family of solitons.
Yeah, yes. So okay, so we just finished finished to argue that the first phase is non-positive. Okay. So next we want to check that the perpar V perp intercept V1 perpar is also non-positive if you assume that your MGH is B-smooth flat. Here we recall that this part is H0, where H is trace free and divergent free. But in fact, we only require H is kernel free in the kernel of divergent. We don't actually use the trace free condition here. Okay, so let me sketch the proof. When you assume the B-smooth flat metric, then we can express our curvature in terms of the capital H or three-form H. So in fact, the cross term related to the curvature part can be expressed as the term like this: 1 over 4 HLJB, HIKB, HIL, HJK. So if the K is 0, we only need to consider this quantity. Here I throw away the gradient V term. I throw away this term. Okay, so this term is something related to the curvature tensor term, right? And this additional Laplacian contains some quantity in the curvature tensor term and the Ricci part. So after simplification, we have this one. Okay, so how to estimate it? We may use the Barkhan formula, Barkhan idea. If you define DH like this, then the DH square will be the gradient H square plus number I HJK, number J HKI. And here, you can use the integration by part and to move this gradient to be here, and then use the commutator formula. So in fact, this quantity is something related to the divergent H square and plus curvature tensor part and the Ricci part. So this is our conclusion. Then we can change gradient H square term in terms of the DH square. so that we will have minus half dh squared plus 2 divergent h squared minus 2 Ricci term. But here, Ricci is 1/4 s squared is always to be positive. So this is non-negative and this is non-negative. The whole term will be non-negative if you assume divergence is free. Okay, so we are done. And yeah, our previous argument didn't give an assumption about the n, but for the n is free case. This result is also followed by the second version we have here, because here psi is 0 and divergence is free. So we don't have these two terms. Every term is non-positive. So the lemma is also true, easy, followed by this equation. Okay, so I think we are complete. We're almost done. Okay, so this is my main result. If you suppose that your MGH is Bismuth flat and Einstein, then MGH is linear stable if Laplacian G is non-positive. Why is Laplacian G? Laplacian G is defining as the half of Laplacian plus 3 curvature term and plus half of Ricci term. This quantity is somehow weird, but I will explain it later. Okay. So following my previous two lemma, we need to consider the variational like this. And if you plug in this variation, we need to estimate our second variation like this. Okay, and for convenience, we will denote our Einstein constant to be mu. Okay, and first, let me focus on the second line. The second line coming from the course term between UG and H. So the first one is coming from UG, and this is H, and this is UGH, cross term and DK. Okay, this term by direct computation, maybe I can skip it, but yeah, if you compute it, you will find that this will be Laplacian U minus 4 mu U times trace of H. But here, we assume our trace is free. So actually, we don't have the second line. And the next thing is a little bit tricky. Okay. Because as I said, this is the hardest one. And we have U dkh plus HIJD KIAB HJAB. How to express this? How to say something about this? So we may try to decompose dk. We want to decompose dk to be something better. Therefore, we will define a three form like this. Lambda AIB to be 1/3, some term H symmetric to tensor composed with a three form. And then we just write, we can write every three form dk to be 3 lambda plus n. N is just arbitrary three form. Yeah, we can always do this. And the reason why I pick 3 is due to the Cauchy-Schwarz. You will find the maximum will be 3. Okay, so if I express this, then there are something will happen. The first, if you compute 1/6 dk squared, this will result in lambda dk minus 3/2 lambda squared plus 1/6 n squared. And due to our assumption, the inner product of lambda dk is the term we want to deal with. Hij, hiab, hjab. Oh, sorry, kab, dk. This is the term we want to deal with. And the inner product of lambda and h is actually 0 because the fact that the trace is free. Okay. So this is really good because here we have this term minus 1/6 dk squared. Therefore, these two terms will be canceled out. We only need to deal with this one. So after simplification, we have these two lines, and by doing so, we don't need to deal with the cross term. As you can see in the second line, because our lambda is only depending on h. So this is only deal with h. And what happened in the first line is here, Laplacian B is the solution of Laplacian U minus 1/6 inner product with n and h. And this is exactly what we did in the V1 case. You just change dk to be capital N. So this whole term will be done positive. Okay. And you may ask what happened in the n when n is 3 case. N is 3 case is really spatial because in this case, our capital lambda is actually 0. So n is actually dk. Therefore, this is always be non-positive. And by doing so, you only need to deal with the term related to h. There are no dk. We don't need to deal with dk anymore. Okay, so next step is we compute the lambda square here, the lambda square. Lambda square is given by 4/3 mu h squared plus a/3 curvature tensor term. Yeah, again, here we use the Bijemu flat condition. Okay, so this is the term we will derive. And okay, so this is how we define Laplacian G. This is Laplacian G, H, and H. We will say that it is stable if Laplacian G, H is non-positive. Okay, so this is the proof of my main theorem. Okay. Any question?
So were you planning to stop there? Is that what you mean?
I think I will start maybe in 2 page.
Okay.
Yes,
Okay.
yes, yeah. Okay, so there's one point I want to mention that you can see that in my theorem, I didn't say that if Laplacian G is negative definite. Sorry, I didn't say that linear stable will implies that Laplacian G is negative semi-definite. It's not true because you can see that the critical point about my computation happens when dk is redundant. So there's a reason why the reason is we may not be able to find a two-form case such that dk is redundant. It may not be happen, but algebraically the upper bound we derive is the best. We use the Cauchy-Schwarz to find the best constant we have. But here we just trick dk to be an arbitrary form. but in fact, D case is not arbitrary. It's the D of something. So it's that maybe there are another way to find a better bound, but we don't know yet. Okay. And the corollary we have, and the example we have is any three-dimensional general Einstein manifold is linearly stable. Because in the n, when n is 3 case, we can claim that Laplacian G is negative semi-definite. And this is to derive this is just a direct computation. Because in three-dimensional case, we can write H to be 2 dVg and the section curvature is a constant. So you can compute easily that Laplacian GH with H is nothing but minus H squared. So this is always to be non-positive. And therefore, three-dimensional GE is always to be stable. Okay, so I think I can stop at here. Is there any question?
Yeah, thanks.
Okay, thank you.
In your results about bismuth flat manifolds, I understand that this analysis of linear stability, you are doing it for arbitrary deformations of the metric, not necessarily compatible with the complex structure, right?
Sorry, I didn't get your point.
Oh yeah, that you are not considering compatibility with the complex structure at all. You are regarding a bismuth flat manifold as an generalized Einstein manifold without any assumption on the variations. So the variations are not compatible with the complex structure.
Yeah, I didn't assume any condition in the variation. Yes.
Well, yeah, of course, those have to somehow be stable in those directions. I guess that follows from what we did.
Yeah.
It'll be interesting to sort that out, I think. Or I mean, I guess to just kind of see it in the structure of the second variation, I mean. All right, so any others? Okay, well, yeah, let's thank Brian again. So
Okay, thank you.